So this is work that Jody Wilson, Harlan Spence, and I published earlier this year in Icarus. Um, I'm not going to get into the chemistry at all. There's one slide at the very end which talks a little bit about that. But really, I'm just looking at what is the radiation dose in water ice on the moon, in PSRs in particular. So galactic cosmic rays, or GCRs, and solar energetic particles, SEPs, they can penetrate permanently shadowed regions. And the reason for this is partly they have very large gyradii in the heliospheric magnetic field. The GCRs in particular have gyradii that are larger than the moon's radius. The more energetic SEPs also do. And then SEPs also follow more closely the heliospheric magnetic field, which can be pretty variable, especially during storm time. And this is just a plot from paper by Colin Joyce back in 2013 of the largest SEP event we've had since Crater has been at the moon. And what you can see is a day or so of GCRs at the beginning, and then there's a big SEP event, and then this little sinusoidal that you see is caused by anisotropies in the SEPs, and they don't get much bigger than this. So for the most part, wherever you are on the moon, you're going to be exposed to GCRs and to SEPs. And in this study, we leverage Crater's unique design. So there are 3 detector pairs. They're the light gray lines that you see here that are labeled with the Ds. And each detector pair is separated by tissue equivalent plastic, or TEP. And this plastic was developed, I think, back in the 60s for the treatment of cancer using radiation, because it's pretty much got the same composition as human tissue. But the cool thing about this is that each of these detectors pairs can measure the dose behind differing amounts of shielding. So the D1, D2 detector pair is the least shielded. So as particles, we're measuring particles that are coming straight down towards the moon. It has just a little bit of aluminum shielding, and that corresponds to about 0.5 centimeter in the regolith. D3, D4 corresponds to around 10 centimeters in the regolith, and D5, D6 to almost 20 centimeters in the regolith. So it's kind of a busy plot. But what this shows is a solar cycle's worth of data that we've now measured, which is super exciting. So you see the 3 detector pairs here, D1, D2, that's the top detector pair, D3, D4 is the middle one, D5, D6 is the one that's at the nadir side of the instrument. And the daily dose in centigrade is over here on the left. On the right, you see the daily dose in 10 to the minus 12 EV per molecule. And just as an aside, other measurements, particularly of meteorites, have shown that the GCR flux has been fairly constant to within about a factor of 1.5 over the past billion years, and it's probably been about similar for SEPs. Let's see, and you can see the solar cycle variation of the galactic cosmic rays. So as the sun got more active towards 2014, all the solar storms erupting off the sun drove the GCRs out of the inner solar system. That's why you see a dip. And now as we're in solar minimum, or we just passed solar minimum, the GCRs peaked. It's kind of the opposite for the SEPs. The SEPs tend to be more prevalent during near solar maximum. And so these are the same 3 detector pairs. And you can see these little curves here. Those are actually GCRs. So these are days that include SEP events. We're actually pretty conservative in determining when an SEP event occurs. This index that I'm using to identify it was developed to identify GCR only times. So it's not as good at identifying SEP only times. But for the most part, about 90% of all the dose that you see in D1, D2 for these events that we've selected, that comes just from SEPs. But then you'll notice there's not as much dose from the SEPs down here, because that's actually mainly the GCRs. And that's because SEPs tend to be very low energy particles, so they're not penetrating as deeply into shielding. And so even if there is an SEP event, most of that is going to be measured by the outermost detector pair, D1, D2, whereas the innermost detector pairs are generally just going to be seeing GCRs the whole time. So we take both the GCR and the SCP dose rate, if you want more information, it's in the paper because I do split it out more. In this talk, I'm just looking at them combined. And then we calculate or estimate the radiation dose, the total dose. If the regolith is undisturbed, the radiation dose just equals the dose rate times the surface age. But impact gardening does create additional shielding. And so the radiation dose isn't going to be as high. It's going to be less than the dose rate times the surface age. And so we use a simple model that we started developing back in 2013 to estimate the exposure time of the regolith as a function of impact gardening. And then what you get is this final plot, which shows aged water ice from 0 to 1 billion years. And then the dose in EV per molecule going from 0 to about 1.2. And that solid curve that's at the bottom, that's what's directly measured by crater. But as you can see, crater's not measuring the full sky. So we extrapolate to include the full sky. And so reality is somewhere in between these two curves. And this is, again, taking into account our fairly simple model for impact gardening. And it's important to point out that there have been studies that have done this. Nathan Schwadron et al. In 2012 and Sarah Kreitz in 2013, they've done this both either using GCR models or observations, again, from crater. But when they, by not including gardening, they actually overestimate the total dose by an order of magnitude or more. So it's a really important process to include. And then I just label on here, Moore and Hudson found that you could detect organics in ice that's been irradiated at about a dose of 1 EV per molecule. So the oldest ice is the most likely to have organic molecules that have been created by energetic charged particles. And along those lines, so this table is from the L-Cross paper in 2010, showing some of the species that were measured in the L-Cross plume. And based on the work by Moore and Hudson, at least 4 of these species can be formed by radiation. And so that's not to say that what's measured there was created just by radiation. There could be stuff that's already there in situ, but radiation processing is an important part of this and needs to be considered. So we've estimated the radiation dose in impact gardened water ice. So it ranges from about 0.1 to 1 EV per molecule. And that depends too on how much gardening there is too over the past billion years. So it's likely that there are organic molecules that have been synthesized by particle radiation. And then again, impact gardening is something that is important to take into account. So thank you for sticking around for the last one.